Hi, welcome to lecture 19 for multivariable calculus. This is an exciting one. We're going to talk about line integrals today. But let's start by reviewing quickly what we should know about every integral we do. We should ask these questions, right? We should be ready to answer them if we come up with an integral. It's certainly something we should pay attention to for every single integral. It's basically three parts. And I think they're neatly summarized by the interrogative pronouns where, what, and how. Okay, so every integral, there's where are we integrating, what are we integrating, and how are we doing it. More specifically, the where is the input values in a domain that we're integrating over, right there. So like this D here, that's the domain of integration. So that's the where. So what setting are we in? What are the points that we're examining here? In a lot of ways, the most important aspect. Remember, this was just an interval from A to B along the real line in Calc 1 and 2, but then we went to two-dimensional objects like solid disks and three-dimensional solids, between two surfaces and so on, and we're going to expand those today. Then there's the what, the integrand itself. This is sort of the only one we talk about in Calc 1 and 2, but it's just part of an integral now. So that's often a scalar valued function, as it was, but we saw with motion, it can be a vector valued function. Right? Acceleration is a vector, and we integrate it to get the velocity as a vector, which we integrate again to get position as a vector. So that integrand, right, very important, but and notice that it comes in kind of different flavors as well. Right? And then lastly is the how. That's the most nebulous of them. Kind of like, how are we adding up all these values? We've got this integrand, some function, and it's defined everywhere in my domain D. And so I kind of want to integrate. I want to add up all those values. But it's kind of like, how can I do it? There's an infinite number in most cases. Well, that's what the kind of differential form here at the end is designed to do. It can give you information, just which variable are we chopping up right here in the case of one variable. But we use like dA for area when we do two-dimensional objects, and we use dV for volume when we do three-dimensional solids for triple integrals there. And that'll become even more important with the new kinds of integrals we'll look at today. Right? So we're going to have some object and values of a function defined along it, and then we want to add up those values in some way, and that little differential form will tell us how to do that here. Still true, all our integrals are Riemann sums, right? There are limits of Riemann sums, so we're going to be adding up value of a function times some measurement, right, in the domain, and we do that all over the domain, and hopefully the limit converges, as it does in most practical cases. Okay, so let's dive into line integrals. Okay, so what makes all line integrals of a kind, right? What makes them line integrals, or perhaps better called path integrals, is the answer to the where question. The where is a curve in space, right? Those curves that we studied in the first part of the course here. So they're images of vector valued functions there. So here's a curve in the plane, and it probably should have kind of a direction associated with that, although we can talk about orientation later. So it's just some curve in plane, right? A set of points tracing out a curve the way you would understand it, or a path, maybe is better. We should recognize that there's a way to parameterize this path, right? The paths we've been talking about have parameterizations, which just means we can write down a function where the input is a single scalar, the output is the position of the curve points, and that's a way of describing where we are along the curve, right? Using a parameter. That's going to be very important for computing along this guy. So all path integrals, line integrals, have this property. The where is a curve. All right. So the first one, that we'll look at are line integrals with respect to arc length. So the where here is the path in space. We'll call that C. Right? And so anytime you see something referred to as a curve, and we often use C for it, down here with a single integral symbol, that might be a clue you're doing a line integral here. The what is a scalar field for these kinds. So F is a scalar field. That's usually defined on the whole space where the curve is. Good one to think about there. Good old temperature in the room. That's a function of several variables, a scalar value function of several variables. And we can imagine a path of some object flying around the room right here. And so at every point of that path where the object flies, it feels some temperature. there. So that's a good setup. And then the how is with respect to arc length. So ds will be our notation to say, oh, we're integrating with respect to arc length. We used s way back when we calculated arc length. So what that means is I've got my path, and I'm going to move along it. I have values of my function at each point along the path. And the way I'm going to integrate those values is I'm going to add up the value times a little measure of the length of the curve, right, at each point. And then I'm going to add up all those products, right? Value of the function f times length of the curve, and I do that for a bunch of different segments. And then I increase the number of segments and do it again, right? So the segments get shorter, right? But there are more of them. And then as they get shorter and shorter and shorter, and there are more and more and more of them, and that levels off when that limit exists. That's the value of our limit. I'll give you a quick interpretation of what this means here. One way to think of this quantity, and so it's this this picture here. So let's be careful interpreting this picture. Our curve in this picture is in the plane. It's down here in the xy plane. If we kind of change the perspective a little bit, you can see it kind of lives down here just in the xy plane. So right, our curve is a curve in 2D. There we can look straight down at it right, from above here. But then we also have the integrand f. So that is a scalar valued function defined on the plane. So that's why our graph's in 3D here. The domain of the function is the plane. Its values were graphed here as the z-axis. Right? But it's important to realize the setup here is that the curve c is in the domain of f. Right? It doesn't like live on the graph of f. It's in the domain, right? Downstairs, if you will. Here. Okay, so what are we doing when we do an integral with respect to arc length in this way? Well, we move along our curve, and at each point we're going to multiply the length of the curve, right? So a little bit of the curve, its length, times the value of the function, which we can interpret as height here. And so if I do that, what I'm really adding up is kind of an area of this curved wall. So as I move along my curve, I'm multiplying the length of the curve times the height of the meaning the value of the function there. And so the result is going to be an area computation, but the area is the kind of surface area of this wall that I'm building. So I hope you see that all the components of our vector field in this wall here. Right, so we've got the curve in from the base. Right, the value of the function f is the height here, and when I add them all up, I get a number. That number could be the surface area of this wall. Right, so if you wanted to ask Richard Serra, how much steel do you need to build one of your sculptures, right? He probably did a line integral to figure it out. Here, Google Richard Serra is fantastic. Okay, so what are the formulas for this one? How do we actually compute this thing? Well, we can start with the Riemann sum form, which you see over here. So we got a sum. We've chopped our curve up into n pieces. Right? On each piece, we add up the value of the function, right, at some point along that piece, right, times a little piece of the length of the curve. So delta S is roughly this one. Right? Now, if you draw a little piece of the curve, let me attempt it to do this here. Right? So we've got some curve looking like this, and we chop it up, right, into pieces here. And so then we kind of want to approximate the length of one of these curves here, right? That's delta S. And we realize that that length there, that's just the hypotenuse of a triangle, of a right triangle here. And the sides of that right triangle are delta x, right? A little division, little change in x and change in y. And so that's where this, right? That's where this expression comes from. And then we can do a clever thing here. So suppose now we've got a parameterization of our curve, r of t. That's going to be very important for computing these guys. What I can do is I can take this quantity here, and I'm going to multiply and divide by delta t Right? I'm going to do it right on top of this formula here. So I'm going to multiply and divide by delta t, but I'm going to bring the delta t inside. So I'm going to multiply by delta t on the outside of the radical, and I'm going to divide by delta t squared on the inside. So I haven't changed the quantity at all, just its form. Delta t squared. But the form is suggestive, because now when I take the limit as I chop my interval up finer and finer, delta t is going to go to 0. Right? So I have a smaller and smaller change for each segment of my curve there. And as delta t goes to 0, right, we start seeing the differential here. Look what happens inside. We see two derivatives. Right? You've got the derivative of x and the derivative of y. Those are the derivatives derivatives of the vector valued function r of t, the function that traces out our curve. Right? The derivative of its two components are sitting right here. So the moral of the story here is when we take the limit, right, as delta t goes to 0, here's the formula we get. If you didn't follow that little derivation, that's okay, right? It's probably worth play it again, see if it makes any more sense. But what you really have to come away with is this formula, right? That makes sense. So on the left, we have the general form for a line integral. I've got all the ingredients. I've got a curve, a function I'm integrating, and I'm doing it with respect to arc length, right? All the information's there. How you actually compute that and come up with a number is you write it as a t integral. So now you're kind of in the t space, just along the real line there. And so what do you add up? Well, you have the values of the functions you get, right, as you trace through the curve. X of t, y of t are the coordinates of your curve. Plug them into f. You get your value of your function, right? Temperature in the example of the old bee flying around the room. And then we've got to make sure we multiply by this guy here. And you should recognize this is the speed, all right, if we have t as time. This is the length of the derivative of r, so the length of the tangent curve here. And that takes into account whether your curve is being traced out very quickly, right? That number will be big if you're being traced out quickly. So right, you get a lot of area because you're moving fast along your curve. And so you're adding up all the arc length that you're obtaining from the curve times the values of the functions you get along. So that's exactly the right quantity to balance those two things. And you see that's where it comes from. Anyway, so this is how you, right? So someone tells you to do a line integral, right? You identify what the curve is, you identify what the integrand is, and you're told to do it with respect to arc length. Right? What you have to do is find a parameterization. Find x of t, y of t that trace out your curve. Find a and b. Those are the endpoints, right? Because usually when we do, if we want to do a finite line integral, we have a finite curve, right? It starts and ends somewhere. So you find values for t to get the start and the end there. Okay, right. So that's what that guy is. We'll do a whole slew of examples in class to get this down. Okay, next kind of line integral, right, moving along here, is not with respect to arc length, but with respect to a coordinate now. So most things are the same as in the last setup. I've got a path in space C. I'm going to integrate my function over that. I've got a scalar value, a scalar field, f. That's what I'm integrating. So it could be the same setup. B flying around the room, temperature everywhere in the room. Right? So the curve is in space. I've got a function defined on that space. Right? That's what f is. I want to add up all those values, right, along the curve. But what's different now is the how. Right? So instead of adding in each segment the length of the curve times the value of the function, now I'm just going to do something actually simpler. I'm just going to say, oh, well, I only care about how one of the coordinates is changing. Forget for the moment why we want to do this. We'll see applications soon. Just rely on what this expression means. So I'm just moving along my curve C. Right? As I move along, I'm adding up the value of the function f times a measurement along the curve, and I'm just measuring it in one direction. Right? So if it's dx, I'm just measuring how much did my curve change in the x direction. All right? So measure that change in x, multiply it by the value f, and add those up over the whole thing. Similarly, right, if you're integrating with respect to y, just add up the change in y there. All right. And so that's the difference. Right? The only difference is in the sum. Instead of adding up instead of adding up lengths of the curve, actual arc lengths there, right, that are always positive, I'm adding up a change in x, and those can be negative, right? That's why these can be a little tricky. But the formula turns out is even easier. If I do a similar thing, right? So I've got some parameterization of my curve. I'm gonna, in terms of t, I can take this quantity and do the same trick, right? But here, there's no radical floating around. It's actually an easier computation. Right? So I just got delta over delta t times delta t there, and you can see what happens now as delta t goes to 0 here. This one will just be x prime, right? So how x is changing with respect to t. That's the only thing that shows up there. So again, right, skipping to the formulas here, right? You've got a curve c. It's a space curve. It's parameterized by x of t, y of t, right? As t goes from a to b. Right? Then the integral over c of f with respect to x is just an integral from a to b. And you take f and you evaluate it on your curve. Right? So there's x of t, y of t there. So that gives you a number along the curve times just the rate of change of x times dt. Right? So we don't have a whole arc length computation here like we did last time, or speed. It's just pure derivative of the first component. Right? So they're actually in some ways easier to compute, these guys. You tend to get formulas that you can deal with better. And that's it. So we add up the same values, but we're basically multiplying by a change in x as we go. Right? Is what happens. For y, mutatis mutandis. Right? Same values, same curve here, but when I'm adding up with respect to y, I need to multiply by the change in y. Right? So that's why y prime shows up. What in the world, right? How do we interpret these guys? So we saw that ds, I said, you basically get an area out of it, right? You get an area of the length of the curve, or piece of the length of the curve times the height at each point. You get like that surface area I constructed earlier. So I can draw a similar picture, but what if we just add up with dx and dy? So here's the same kind of drawing, right? But I've got three colors now, right? Red is the one you already saw. That's with respect to arc length. Blue is going to be the interpretation of adding up the values of my function and times the change in x, and y, of course, is green, the change in y. And so we're going to see those are basically projections onto the surface. So let's see what happens here. So, all right, I've traveled along my curve. Here are the three things I've added up, right, with respect to arc length. Right, that's the red bit. Right, so I'm getting the area of this whole curved wall here. For dx, I only care about how x is changing. So I'm drawing the shadow of this figure in the x direction. So I'm adding up the same values of f, of course, show up here. But I'm adding it up times the change in x, which seems to be negative here. Right? So if I were to stop integrating at this value, part of my curve, I'd have a negative value for the derivative with respect to x right here. And notice with y, I've got a very small value. Right? Y hasn't changed very much. Right? In aggregate, I'm not even sure if it's positive or negative here. Right? See that y, it hasn't changed all that much. So even though f has the same values were integrated, we're going to get a smaller integral here if we integrate with respect to y. Let's just keep going, right? And you can kind of watch the projections happening right on the walls here. Blue is x, green is y. And I'll just pull it all the way up. I want to go around. So notice, right, we do need to think about signs here, S-I-G-N, signs. With respect to arc length, if we're integrating a positive function, we're always going to get a positive integral, right? Because ds, right, you saw that radical, right, sum of squares in there, always positive there. So the integrand f can be negative, right? You can have temperature below 0 right, here. But if the thing you're integrating is positive, you'll always get a positive number with respect to arc length. Not true with the other guys, right? We got to be careful with dx and dy. You kind of can see in this picture that they sort of go back and forth, right? X gets traced out going one way or the other, right? The sign in x prime of t, right, will add when you're going kind of to the right in the positive x direction. It'll subtract when you're going against it there. Okay, just remember that with dx, dy, we get aggregate answers, kind of net answers from adding things up, whether we add them up in one direction or the other. Right? With respect to arc length, that doesn't happen. Okay, so there's your picture. All right, that's about it. All right, third, last kind of line integral. We're gonna see, here's where the what changes. So it's a line integral, so it's over a path. That's the same in everything we talked about in this video. The what changes now. So instead of integrating a scalar field like temperature, there's a vector field around. Again, think of like wind. And so I want to sort of integrate wind as I move around on some path here. So what in the world does that mean? Well, the last question is, how are we integrating? What am I going to do? I walk along my curve. Okay, I find an arrow at every point. Right, the wind is blowing somewhere. Right, at every point. Every point's a vector. I want to kind of add up all of these here. But what I'm going to do is not literally add up all those arrows, since there are an infinite number of them. I'm going to add up a quantity, and I'm actually going to come up with a scalar here. The scalar I come up with is I'm going to integrate with respect to the direction of the line dr. This sounds complicated, but it's sort of a natural thing to do. So I'm moving along my curve. At every point, I find a direction from the vector field from the integrand. So think about wind right here. So I'm walking along my curve in one direction. The wind can be blowing in some other direction right there. And a way to integrate those values, say, okay, well, how much is that wind, is that vector field pointing along my curve? Right. So the way I think of it is how much is it helping? Right. So if you're running a race and it's there's a question in track and field events of whether a race was wind aided, right? Did the wind help the athlete run down the track faster? That's kind of what a line integral of a vector field is measuring, right? How much did the vector field help? And so the way it does that is our old friend the dot product. It's back from the beginning. Right? Things kind of click together really nicely here. I'm walking along my curve. F is the vector field, right, pointing in some direction. My curve naturally has a direction from the tangent vector. Right? So every time we parameterized a curve R, if it was smooth, it had a tangent vector R prime of t. And so I want to measure how much the vector field F points in the direction of the tangent vector. That's what the dot product does. Right? Do those things agree or not? Right? So that's what the dot product measures. I've got the two vectors there. Right? It's kind of like naturally sitting there. What should I do with them? Right? Dot them. Right? You get a scalar out of that. Add up that scalar over the course of your path here. All right. So another way to interpret this, right? If F is a force, right, and so along your path, then you're measuring about some force, and it's pushing right on you as you travel some path, right? You don't always go in the direction of the force, right? Think about a wind blowing on a sail. Right, when you're sailing in the ocean, you want to go one direction. You can use the wind that's pointing another direction, right? You can tack into it, and you can go in the direction you want to go while the wind pushes in a slightly different direction. Right there. When you do that, what you end up measuring when you take this integral is work. Right, work is force times distance here, but so you went a certain distance along a path, right? But you're not just multiplying the force. The magnitude of the force times the distance, right? It's how much is the force pushing you in the distance you're going, right? So you do get this dot product, F dot dr, gives you what you want. And then the question of wind assisted, a little link in the slides you can follow about what does it mean for a track event to be wind aided. For marathons, it's a whole different consideration than it would be for short track events. Here, neither here nor there. So show you a picture. Right. So here's a picture of two curves. Right, I got a blue curve and a red curve. So I got one vector field. It's this circular vector field, and I've got these two curves, right, blue and red, or I hope it's red. I'm colorblind. Here. So let's imagine we're traveling counterclockwise, so right from right to left along these curves. And I just want to compare what would the line integral of this vector field that I see here, right, over these two curves, how would those two line integrals compare? So what we're adding up, of course, is how much the vector field points along the direction. It's a dot product, right? F dotted with the direction of your line. And of course, the bigger the magnitude of f, the bigger number you're going to get. So if I look at the blue one here, notice that it's got large arrows, or larger, everywhere along it, and it lines up perfectly, or more or less perfectly, with the vector field. I'm going to get a big number from the integral of the vector field along the blue line here. Notice the red line, it's a more direct line in distance-wise, but that's not what we're measuring when we do a line integral of a vector field. Right? Along the red line, I'm got to think about all the dot products here, right? Of the arrows I find when I go along from the vector field, how much do they agree with the tangent vector here? The tangent vector is constant for this guy there. And you see that, oh, well, they kind of agree there. You see acute angles. They sort of push in that direction, but they have small magnitudes, and they don't push perfectly along it, right? Look over here, right? They make some angle there. So maybe push it a little bit, but not that much. You're going to get a much smaller value along the red line is what it comes down to for this guy. So that's how you should, right? That's a good way to interpret a line integral of a vector field. So you've got a path again, you've got a vector field present, right, along that path, right? So f and the path, they can be independent of each other. Just as you move along the path, you see this vector field f. So what do? You dot them and you add it up. So what does that mean formulaically? Right here, right, move along my curve. There's the value of the vector field here. I'm going to dot it with the change in x and the change in y of my curve there. And same trick works here that we've worked on every one. This thing's a vector now, but I can still scale a vector. Right? So I can scale by 1 over delta t and move it inside. Multiply by delta t on the outside, so I haven't changed anything when I do this, right? I just put it in this form. So then I can see what happens when delta t goes to 0 now. I chop my curve up finer and finer here, right? This becomes just the derivative, right? There, r prime of t. I've got x prime of t, y prime of t as a vector now. So this is kind of neat, really nice and compacted. Brings things together. I've got a vector field, I've got a curve, and so the thing on the left, just use that as notation. Don't compute using the thing on the left, right? What I mean by that, that's kind of just notation to tell the reader, hey, here's what I'm going to do. I'm going to do a line integral over C of a vector field f at the points along here. The way to interpret is move over to the t space. Right? What I mean is find a parameterization for your C, right? And then plug it into f, find its derivative, right? Dot it, right? And if that looks like the chain rule, right, or something resembling the chain rule, you're ahead of the game, right? That's coming here. But anyway, if we know f and we know our parameterization C, we can just plug in for these guys. You'll end up with one integral in t, right? And that's something you can do from Calc 2, or better yet, grab a high school senior off the street and make them do it. That's how I compute most of my integrals. All right, quickly, just to kind of reunite this back with things we've seen before. All right, if we just look at some notation here, like f has 2 components, p and q, that's typical now. Right? This is going to be a real alphabet soup again. Right? Remember, f is a vector field. Right? So at each point, it has 2 components in the plane anyway. So p is the first component, q is the second component. Right? Okay, so then when I write this out, right, remember that this f, that's p of x of t, y of t, right, dotted with it here. What happens is we can expand out this dot product here. And again, I'll try not to abuse my my mouse handwriting here. So f, right, is components p and q. I dot them with x prime and y prime. So x prime goes with p, of course. So I get p x of t, y of t, y prime, I mean x prime, y of t, x prime of t, right, dt, right, plus blah blah blah, right? You know what's coming, plus q of t and so on. I don't want to stop, but look at this form. I've got a function P is a scalar valued function, x of t, and I see x prime of t dt here. It's exactly what we called, all right, the integral of p with respect to dx, and then the integral of q with respect to dy as well. And so they're the same thing. It links it back up. The integral of a vector field is the sum of two integrals with respect to the coordinates, and that's really where the coordinate thing comes in. It looked a little strange when I was doing those projections, right? The red and the green and the blue. And so on, right? They often come from vector fields, which have more real-world applications. You can imagine work integrals, right? You've got and not just in wind fields, right? In electric fields and magnetic fields and all sorts of other fun things. Gravitational fields, of course. Okay, and then one more here to connect it back to line. If we remember that t is the unit tangent vector. Right, so that just means the direction of your curve, but made into a vector of length 1. Then I can rewrite the dot product this way. Right, so then r prime of t is just, right, capital T times the length times the speed here. And this is another way of interpreting it. So these two are the same thing. Right? Let me circle those so that you can see them. This guy here, line integral of a vector field, right? That's the new notation we answered. This we could have interpreted, right, carefully in the beginning of this video. So the integrand here is a scalar. It's the dot product of the vector field with the unit tangent vector, but then integrating with respect to arc length. Right there. So this is useful for interpreting what this guy is. The thing in the parentheses here is a scalar. It's a projection. Right? It's projections back. It's the projection of the vector field along the curve. Right? So done at each point. Right? So you project it along the curve. So you use a unit vector for your projection there. Right? But then you add it up with respect to arc length. All right. And that's that. Right? So we've got, right, to sum up, we've got 3 kinds of line integral that we've seen, right? So the line integral is new. What unites all 3 kinds is that they're all happening over a curve, right? C. Right? This can be in the plane, it can be in space, it can be in higher dimensional space if you like. So all 3 kinds happen over, right, over a curve. But then the other things can change, right? You can integrate a scalar with respect to arc length, right? You add up the scalar times the length of the curve. You can integrate a scalar with respect to a coordinate, right? So the integral over c of f dx, we're going to add up the values of f times x prime of t dt to get an answer out of that. And then lastly, we can integrate vector fields, right? And the way to do that, integrating a vector field over a curve means you take a dot product at each point with the vector field and the tangent vector of your curve, and you add those up over your whole interval. Right? So this formula up here is perhaps the most important. All right. In class, we'll dive into a ton of examples. Hopefully this stuff will make a bit more sense. We'll do some work examples as well, right? Something a bit more real world. And then when I said you're hinting, I kind of see that it almost reminds me of the chain rule. It's not the chain rule, but it reminds me of the chain rule there. Well, then we're gonna exploit that as well. All right, see you tomorrow.